is free to take like 1-2 minutes to go to grab some coffee, tea, whatever he or she wants to grab. But I think Andrea, you are ready, right?
Yeah. Can you see my slides?
Yes, we are. We see it.
And can you hear me well? I have very precarious IT equipment.
Yes, we hear you well.
Okay. So 2 minutes.
So, Serежа, will you start recording right now, right? What?
I have started already, yeah.
You started. So let me present the next speaker of our first day, Andrea Brini from now University of Sheffield and CNRS. And Andrea, again, you see, will tell us about stable maps to something that I cannot pronounce, never tried. Can you?
Looijenga is the correct Dutch
Bravo.
pronunciation.
Thank you. I'm just gonna murder this pronunciation for the whole duration of the talk. Okay, so first of all, I would like to take this opportunity to advertise something that's that we're gonna have in Sheffield in a little less than a month from now. So we also had a conference last year that had to be postponed because of the pandemic, and we're gonna carry out online. There's lots of exciting lectures and talks by many of the usual suspects in our business. And yeah, the registration is the deadline is the 18th of June. So be sure to sign up to get the Zoom link. And yeah, I'll look forward to seeing many of you there. Right. So starting with a talk proper. So can you see that my slides are changing? I'm always worried about that. Can you see I'm moving from one slide to the other?
Yes.
Yes.
Okay. Well, good.
And I will distribute your slides to.
Oh, thank you. Yeah. Okay. So let me first of all explain the title of the talk. So the main character throughout this talk will be pairs XD, which are log Calabi-Yau surfaces with Neff maximal boundary or Neff Looijenga pairs. And this is code for the following. I'm going to have X, a smooth complex projective surface, and D, a singular divisor, which throughout this talk will always be anti-canonical, and with a decomposition D1 union DL, with L greater than 1, with simple normal crossings, singularities. And each irreducible component Di will be taken to be smooth and Neff. So if this doesn't resonate with you, think X is going to be a differential geometrically. X will be a compact 4-dimensional Riemannian manifold equipped with a compact Riemann surface, a singular compact Riemann surface stuck in it. And all these conditions about D being anti-canonical and the existence of this decomposition amount to say that this Riemann surface D looks like a necklace of P1s that are joined together through some mild singularity, like a node. So for all practical purposes, you can think of X being projective plane throughout my talk. This will be my running example, and D to be the union of a line and a conic. So a toric genus zero curve and a non-toric genus zero curve intersecting at 2 points. So this would be my characters: complex surface and a curve in it, singular curve in it. And I will try to convey the following 2 main messages. So I'm very happy to give away my punchline before it gets too late in the talk. I want to claim that there exist several enumerative theories of curves that are constructed out of X and D. that have superficially very distant flavor from each other, but they are nonetheless related. So the resulting invariants are essentially the same, or they're related to one another by some definite relation. That's the first message. And these are, most of these are rather unexpected. And the second message of the talk is that I'm going to use the fact that there exists this web of relations between different enumerative invariants of these pairs X and D to solve them all in closed form. And this joint work, which has appeared at the end of last year with Pierre Dussault in Saclay now, and Michel Van Gorel in Birmingham. And it includes bits of ongoing work with my student, Yannick Schula, who's in the audience right now. Okay, so if you know what these names mean, what I'm going to claim is that there's a relation between the log Gromov-Witten theory of the pair and the local Gromov-Witten theory of it. And I'm going to introduce an allied theory of open Gromov-Witten invariants that's related in a definite way to the log theory. And I'm going to use this as a sort of gateway to uncover new relations to different classes of Donaldson-Thomas and BPS invariants. If you don't know what this means, no panic, because I'm going to start very slowly now. So there's one of the driving motivation of the theme of this talk is a very ancient problem in geometry, and a very modern one as well, namely a class of enumerative problems. That's a subset of questions in geometry where you ask yourself how many configurations in a given space satisfy a number of given geometrically meaningful constraints. And of course, this dates back to Greek antiquity, like with Apollonius' problem. And it arises very fast to very modern problems of research in our field, which are still open. So examples of classical questions in enumerative geometry are, well, the 27 lines on a smooth cubic surface, or closer to the heart of this audience, how many genus 0 degree D curves in the plane pass through 3D minus 1 points in general position, or even more complicated, how many degree D curves of given genus exist on a quintic threefold. And one thing that these three example questions have in common is the fact that I'm always counting curves. And throughout my talk, I'm going to count complex curves in complex varieties. So we're dealing with counts of one-dimensional objects in a given target algebraic variety. And this obviously has an intrinsic motivation in geometry, but it also ramifies to other domains of mathematics, mathematical physics, like relation to integrable systems, low-dimensional topology using string dualities relating to Chern-Simons theory, generating functions of these invariants have wonderful properties, and they're sometimes related in natural variables to modular forms, and you name it. I think we're all diehard fans of this topic. And so how do you phrase an enumerative problem? Well, the typical setup is you start with X, some smooth projective algebraic variety, for example, the complex plane. And suppose you want to answer question 2 in the previous slide for degree 2. You want to count conics in the plane that pass through 5 points in generic position, so no 3 collinear. So what you would do is you would construct an auxiliary geometric object that parameterizes your curves in your target variety. It's a moduli space of curves in X. For example, plane conics, so space of quadratic polynomials, homogeneous degree 2 polynomials with not all coefficients vanishing. So that's a linear space of dimension 6 modulo C star, and it's just P5. And now you would like to extract from this moduli space some numbers. by intersecting cohomology classes that represent the geometric constraints that you're looking at. And so the so-called quantum invariants. And so for example, in the case of the conic through 5 points, you're solving 5 linear conditions for your 5 degrees of freedom. That's like intersecting 5 times the hyperplane class in P5 with itself, and the result is 1, as is well known. And this is something that we would like to do systematically whenever we have an enumerative geometric problem of curves of some type. But we're almost never so lucky to have a situation like this. So the moduli space we deal with will often be non-compact, and different compactifications of this moduli space will lead to different types of invariants that are nevertheless related in some way. For example, well, Gromov-Witten invariants, Poisson-Mach invariants, DT invariants. And well, throughout this talk, my theories of curves in a variety, I will always think of them as parametrized curves. So I will try to codify my problem in terms of moduli spaces of morphisms to X from a source Riemann surface, algebraic curve. So I'm going to consider moduli spaces of pointed curves of given genus, along with morphisms to my target variety X of fixed degree, modular automorphisms of the domain. That's my M bar of X that I'll consider with some variations throughout most of my talk. And well, the compactification, that's problem number 1. The way we solve this is what we consider Konciewicz's compactification. That's what this big overline means. And we replace the condition that our source curve is smooth by imposing that this is nodal and including some stability condition. Basically, we're only ever allowed to contract an irreducible component of our source curve C when this is stable in the sense of stable curves, or stability for curves. And this moduli space has lots of pathologies. It's singular, it's not equidimensional, but at least the compactification does what it says on the tin. It gives a compact moduli space of given expected dimension, dimension of the target space minus 3 times 1 minus g, plus the anti-canonical degree of the image of my curve, plus the number of punctures. And even though it's singular as a scheme, it carries a perfect obstruction theory, and it supports a virtual fundamental class in the expected dimension. And so the answer to my enumerative theoretic problem of, for example, counting degree D genus G curves in X through a given collection of cycles, B1 through Bn, can be approached by, well, we have canonical evaluation morphisms given by the fact that we have punctures on this moduli space. We can use those to pull back the classes of Bi, I from 1 to n, and we can intersect against the virtual fundamental class. And if we're lucky enough, the numbers that we get are enumerative significance, and we can remove the scare codes. And one example where this happens is the example of the second question of, I think, my first slide. What about the number of rational degree D plane curves through 3D minus 1 points? In this case, we take X to be P2. We're looking at plane curves. They're rationals of G is 0 and of given degree. And we pull back 3D minus 1 point condition and intersect against the virtual fundamental class on this moduli space of stable maps. And in line with the spirit of the time, I'd like to hit the audience with a big, relatively big table of numbers. And this will be justified later. So with these, we have some very well-known numbers that we see on this table. Like if we consider just d equals 1, we're looking at a line through 2 non-coincident points. We know very well that we have just 1. And if you consider degree 2, once again, we're looking at plane conics through 5 points, not rectilinear. And as in the previous example, this amounts to solving some linear problem when these points are generic that has maximal rank. And therefore the answer is unique. You get 1. And there's some nonlinearity kicking in when we go up to degree 3. And we're looking at cubics. And the reason for that is that not every cubic in plane is rational. In fact, they occur in codimension 1. And that's a nonlinear condition in the coefficients of the polynomial that defines them. So if we want to count those, essentially by Bezout argument, we're intersecting a cubic and 2 quadrics in projective space. So 2 times 2 times 3 is 12. And the problem gets more and more difficult when we increase this degree d. And 2 things that I would like to say about these numbers are, well, first of all, they grow very, very fast. And we can estimate how fast they go. So they asymptote to 3d minus 1 factorial times some complex number x0, to the power d. So they have an exponential power law once we take a Borel transform. And after 25 years, we don't know yet what this number x0 is. So they seem to be quite wild beasts to analyze in all degrees. And what we have is that we can determine them all. So these were known up to degree. So degree 5 was known in the mid-80s. And what Concierge discovered in 1992 was the existence of a nonlinear recursion, which, when expressed in terms of generating functions for these numbers and d, gives a particular solution of the Paine-Levé-6 equation. So even though the geometry seems particularly simple, the numerology and, in a sense, the mathematical physics that's behind this is quite intricate. And I would like to contrast this with what I'm going to show in a moment. So this is a very familiar setup to many of us, and I would like to discuss something that is slightly less familiar, perhaps. And I would like to do so by stepping up my game a little bit. And I will not only consider now invariants coming from stable maps to a variety X, but I want to introduce invariants of a pair XD. So the invariants will feel an extra ingredient given by this D, where X is again smooth complex projective algebraic variety of dimension M, and D is a singular anticanonical divisor with relatively mild singularities, just simple normal crossing singularities. And it can be presented as the union of L irreducible components, each of which is required to be smooth and nef, so intersecting non-negatively any effective curve in X. So the simplest example is we start with M equals 1. So X is one-dimensional, and we can take X to be P1. And in this case, D can be taken to be for L equals 2, just the union of 0 and infinity. And something more interesting for M equals 2, we can take X to be the projective plane. And for L equals 1, since we insist that each irreducible component is smooth, if we require that D is irreducible, then it is forced to be a smooth cubic in P2. Or for L equals 2, we have a slightly more degenerate situation where D is the union of a conic and the line not tangent to it, so intersecting it and in 2 points. Or the sort of maximally singular situation in this setup is to take L equals 3 and D the union of the coordinate axes, so the union of the toric divisors in P2. Now, some terminology that I will use consistently more or less. A smooth Neff pair XD will be called toric if X is a toric variety and the complement of D in X is the big torus orbit, C star to the M. And I'm going to call XD a Looijenga pair if X is a surface and D is singular, which again, by the previous definition, implies that L is greater than 1, so D is reducible. Now, the Neff Looijenga pair is tame if either it has either more than 2 components or each irreducible component has positive self-intersection. And this sounds like a bit of a technical condition at the minute, but I'm going to justify its implications in a moment. Now, if you look at the constraints of being a Neff Looijenga pair, we get and smoothness of X, we get a finite catalog of smooth deformation families of Neff Looijenga pairs, most of whom are tame. So there's 18 deformation families, and only 3 examples are generally non-tame. And for the rest of my talk, I'm going to stick to these Looijenga pairs. So X a surface and D a simple normal crossing divisor in X with Neff irreducible components. And I said that I wanted to step up my game a little bit, and I want to introduce some Gromov-Witten-like, actually genuine Gromov-Witten invariants that fill the geometry of the pair X and D. And I'm gonna do it in 2 ways that a priori have nothing to do with each other. The first thing that I would like to do is I start from X, and I consider the direct sum of the dual line bundles to the irreducible components di of D. So because we have L of these irreducible components, I'm looking at a rank L vector bundle on a surface X. So this total space is a 2 plus L dimensional complex quasi-projective variety. And because D is anti-canonical, this total space is Calabi-Yau. So there's a non-compact Calabi-Yau 2 plus L dimensional variety that I construct out of X and D. And what I want to compute is what are the genus 0 Gromov-Witten invariants of this total space. So naively, this is the number of degree D genus 0 curves in this total space EXT that pass through the appropriate number of points in it, equal to the expected dimension of the corresponding moduli space. So for example, in the case of the line at the conic, I'm considering a total space of O-1 plus for the line plus O-2 for the conic over P2. And that's a non-compact Calabi-Yau fourfold. And I want to compute its Gromov-Witten invariance. And well, we know the drill, which should construct some compact moduli space that parameterizes these objects. And the condition of Neffness ensures that whenever a stable map to X intersects non-trivially the divisors di, then it can't deform holomorphically of the 0 section of this total space. So scheme theoretically, the moduli space of maps to the total space is just the moduli space of maps to the 0 section, to the moduli space of maps to X. However, the 2 obstruction theories differ, and this is encoded into a canonical obstruction bundle on this moduli space. And the virtual fundamental class of for the total space is given by intersecting with a top chain class of this obstruction bundle. And this cuts down the dimension to L plus N minus 1. And once we have this, we can define the local Gromov-Witten invariance of X and D, or the Gromov-Witten invariance of the total space, by just pulling back point conditions from the target in the appropriate number, which is L minus 1, in order to get a non-zero number, and capping against the virtual fundamental class. So that's one set of invariants constructed from X and D. And the second set of invariants that I would like to construct have a very different flavor. I don't want to use D to define an embedding into a higher dimensional Calabi-Yau variety, an embedding of X into a higher dimensional Calabi-Yau variety as the zero section, I want to use D to impose some kind of boundary conditions on my maps. And I would like to compute, again, scalar quotes in order, the number of degree D rational curves in X that pass through L-1 points and have maximal tangency at each of these divisors, Di. So again, in the running example of P2 with a line union and a conic, I would like to compute the number of degree D genus zero curves in the plane that pass through one point. And so these will intersect generically a conic in 2D points and the line in D points. What I'm going to impose is that I want to sit in some higher codimension setup where this point, I'm going to be in the maximally degenerate situation where this point is unique, and it has maximal contact order. So 2D with a conic and D with a line. So again, the drill is, well, we want a moduli space that parameterizes these objects, and hopefully it's compact and will carry a virtual fundamental class. And we will define the Gromov-Witten invariants by suitable caps of pullbacks of evaluations of classes against it. But this is a lot tricky. It's a lot trickier than the previous case. There's immediately a problem with compactness, as if you think of a sequence of stable maps with prescribed tangency order against some divisor, then in the limit, these can have irreducible components that can fall entirely into it, so that in the limit, the notion of maximal tangency doesn't have any meaning. And there are different regularization schemes to take this into account. Will overcome the problem either in symplectic geometry or well, in algebraic geometry with Jun Lee's theory of expanded targets. They all consist of doing something to the geometry of X. And in the case in which D is singular, it turns out that the most effective way to produce a sensible curve count is to resort to log geometry. So we view X as a log scheme for the divisorial log structure given by D. And in this case, there's a well-defined moduli space of log stable maps to the pair X and D, where one essentially comes to terms with the fact that we can have maps that in the limit have components that fall entirely into the divisor by remembering the notion of contact order in terms of some homomorphism of between ghost sheaves. And so this is proper, and it has expected dimension the same as for the local problem. And under some minimal set of choices, this carries a perfect obstruction theory and the virtual fundamental class in the expected dimension. And that's the last step of the constructions of Gromov-Witten theory. We can compute Gromov-Witten numbers that hopefully answer our question, our enumerative question, by pulling back point conditions from the target and capping against this virtual fundamental class. So we have these two sets of numbers from our pair, surface and divisor, anti-canonical, singular anti-canonical divisor in it. So what was the purpose of showing you the Konciewicz numbers of P2? I can show you what these numbers look like. For example, for the case of the plane with line union conic. And so the first thing that that catches well, that caught my attention is these grow a lot more slowly than the ordinary invariants of P2. So they grow exponentially, not factorially. So in particular, the generating function is not just Borel summable, it's convergent. And as a matter of fact, while the Gromov-Witten invariants of P2 were very difficult to determine, if not recursively, we can find a close formula for these. So these look like, and in fact are, the central binomial coefficients. So up to a linear factor of Catalan numbers, 2D choose D. And so even though the geometry is much more complicated, the numerology seems somehow simpler. And one thing that also looks quite simple is the ratio between the log and the local calculation. They're not entirely unrelated, and they're related in a very simple way. There's just a sign, and we can tell what this is going to look like. We have an alternating sign, a factor of 2, and the rest is just a quadratic row, which is actually quadratic for all degrees. And this is even simpler in the a priori more singular setup of P2 relative to the union of 3 lines. In this case, these numbers are not mysterious at all. They are what they seem to be. So they grow quadratically, and they are actually just d squared. And again, the ratio between the log and the local calculation is some alternating sign times, in this case, we have 3 divisors and we have a cubic low. That's interesting in this example. And it turns out to be fairly generic. So people have tried to work through, well, a bestiary of some examples. And the fact that the log and the local calculation, even if they are geometrically completely unrelated, they just take the same input data, they seem to be related by a law of the type sign factor times intersection multiplicities. And this was codified as a conjecture 3.5 years ago by Van Garel, Graeber, and Rudert, who claimed that this always happens, that the log calculation is equal to a universal factor, essentially, just a topological factor times the local one. And this is given by the product of intersection multiplicities of our stable map D times -1 to the intersection multiplicity +1. Okay, then the question is before we even assess the question whether this is true or not, there's a lot going on even by just assuming the existence of a formula like this. Now, by definition, the local invariants were the trickier one to define. They involve log geometry, and they have much more limited tools to be computed, but they do reflect something that you can explain to high schoolers. So you're just enumerating curves in some target with some tangency conditions on a given collection of curves in your surface. As a matter of fact, the conjecture is not restricted to surfaces. It works it was made in all dimensions, and but they're very hard to compute. So they're beautiful but hard. And on the right-hand side, we have these local invariants, which are Gromov-Witten invariants of higher dimensional Calabi-Yau varieties, for which we have a lot of tools from, for example, local mirror symmetry. So these are, their numerative significance is more difficult to decode, but we know how to compute them. So this is an inequality that basically states that beauty is equal to power, if it's true. So is this true? And well, the evidence in its favor is that it is true when D is smooth. And this was proven by Van Garel, Graeber, and Rudert in their original paper. And then about a year later, Pierrick, Michel, and I proved it for toric pairs. So where X and D is a smooth net toric pair. So this is some evidence. And for the purpose of my talk today, I want to ask, is this true for Looijenga pairs? So X is a surface and D is singular. And I claim that both the descendant log and local Gromov-Witten theory of net Looijenga pairs with point insertions is closed form solvable. And in particular, the log local correspondence holds. Let me give just a sketch of the proof. Leonia, what time did I start? Was it 20 past?
Approximately, yes. So
approximately, okay. Yeah, so probably I have time to give just a bit of a sketch of the proof. Well, on the local side, the Gromov-Witten theory of the total space can be reconstructed from that of X from by now classical theorem of Coates and Giventhal. And so the question is, how much do we know about the geometry of the Gromov-Witten theory of X? And for Looijenga pairs, it turns out that we can always use a deformation argument to reduce the calculation of the one-pointed Gromov-Witten invariance, genus 0 Gromov-Witten invariance of X, and therefore of the total space, to some toric setup. Perhaps at the price of enlarging the pseudo-effective cone by some -2 curves that become effective, that contribute non-trivially to the mirror map. But we have some kind of toric mirror symmetry statement, provided we can invert the mirror map. And the sort of miracle that happens is that the mirror map is closed form invertible for all Looijenga pairs, non-trivially, but true. And so this gives an explicit non-hypergeometric closed form for the Gromov-Witten theory of for the one-pointed invariance of the total space. And for the multi-pointed invariance, this can be determined essentially by using WDBV in the big phase space. So there's some vanishing result of for big quantum cohomology that allows to reconstruct big quantum cohomology from the small one. And the notion of tameness that seems completely technical, so more than 2 components or positive self-intersection, is synonymous in this context to triviality of the mirror map. So those are the simple cases from the point of view of mirror symmetry. And the result for the case of P2 with a line of the conic is, again, the central binomial coefficients with that prefactor of Van Grael-Graeber root delta. Now, on the log side, the theorem is proved in 2 orthogonal ways. So any Looijenga pair has either 2 components or is tame, or possibly both, like in the case of P2 with a line and the conic. So for L = 2, we have a degeneration to the normal core argument that allows to prove a comparison theorem between the log and the local invariants, giving the correct prefactor. And for the tame cases, and again, L = 2 and tame, the union of these gives the whole set of smooth net Looijenga pairs, can be solved explicitly using scattering diagrams. And in this case, the notion of tameness is synonymous to having finite scattering. So once again, we have, in the first case, we have a comparison theorem and deduce that we can compute all the log invariants in closed form from the solution of the local. In the case of tame, we can solve both the local and the log invariants separately, and we can deduce the log local correspondence as a corollary. So that's the end of a story, at least. So we have these 2 classes of invariants for Looijenga pairs. We can either determine them completely, well, we can determine them completely, and we can deduce that the original log local correspondence of Van Grael-Graeber root that holds. And that's it. Were it not for the fact that we can do a lot better on the log side. And this stems from work of Pierre Bousseau's in his PhD thesis, who pointed out that the sort of tropical calculations that arise in the scattering calculation for genus 0 can be uplifted. So as a matter of fact, we can bootstrap all genus results from knowledge of the genus 0 Gromov-Witten invariance alone. So because we're dealing with surfaces, the expected dimension of the moduli space of log stable maps to X and D goes up by G when we consider genus G Gromov-Witten invariance. So if we want to extract a number, we need to cap with something. And the usual way we would do this would be to, in Gromov-Witten theory, would be to add some extra punctures and pull back more cycle conditions so that we can get a number after capping with a virtual fundamental class. What another thing that we can do to reabsorb this excess dimension of equal to G is to cap with some natural cohomology class. And it was discovered by Pyrrhic that if we cap with a top chain class of the Hodge bundle, lambda G class, with some sign, and we construct some generating function in a variable Q. So log Q is what we would usually call H bar, the genus counting parameter in Gromov-Witten theory. Then the scattering calculation of n log gives as a 0f for spin-off a calculation for this all genus Gromov-Witten generating function to all genera, just by promoting the tropical multiplicities to their block-Kötsche counterpart. So just their Q analogs. And so not only do we have access to the genus 0 log Gromov-Witten theory of smooth Neff Looijenga pairs, well, tame Looijenga pairs for the scattering calculation. We have access to the full higher genus theory, just without making any effort. And a sort of natural answer, well, a natural question that one would like to ask at this point is, what is the local counterpart of these higher genus invariants? And what is the higher genus log local correspondence? What would it look like? How is it modified? And the answer to that is that it doesn't even make sense to ask the question. If, for example, if you deal with a surface with twisted by a vector bundle of dimension greater than 1, you're looking at a Calabi-Yau n-fold with n greater than 3. And for these, the expected dimension becomes negative when the genus gets greater than 1. So there's a well-defined notion of genus 1 Gromov-Witten invariance without any punctures. But then the expected dimension decreases as the genus increases. And in particular, there's no higher genus local Gromov-Witten invariance to play with for starters. And there's a bit of tension between what we can do on the log side and what we can do on the local side. And so this was the beginning of a long list of headaches. And our proposal to solve them was that these local genus 0 local Gromov-Witten invariants of Calabi-Yau n-folds, where n is 2 plus L, should really be looked at as some sort of genus 0 open Gromov-Witten invariance of some special Lagrangians in a Calabi-Yau threefold, somehow in Schick's clothing. And they're actually equal on the nose without any prefactors or anything. And unlike those local invariants, the open invariants make sense in all genera. And these are the candidates to replace the local invariants in higher genus and produce an analog of the log local correspondence for higher genera. So somewhat schematically, there's a symplectic heuristics behind it, where, well, we could look at a meromorphic function on a curve with prescribed ramification profile at infinity as some sort of degenerate version or limiting version of a map from a compact Riemann surface to the unit disk with prescribed windings around each boundary component. So in this case, when we consider what this would look like in the context of log Gromov-Witten theory, the expectation is that the relative theory with maximal tangency along the divisor should be a sort of limiting version of the open Gromov-Witten theory with boundaries on some special Lagrangian that is near the divisor, with winding equal to the tangency. And when you want to make this slightly more rigorous and look at it in terms of Gromov-Witten counts, you see that you should multiply by a factor which is exactly the same as the one that Van Garel, Graeber, and Root find. So open Gromov-Witten invariance should match on the nose with a local invariance in this setup where we replace maximal tangency with open conditions. And there's a physics heuristics behind it as well, specifically for L equals 2. Now there's a very well-known beautiful story that probably Gaetan will touch upon tomorrow with this talk, that relates the Gromov-Witten, genus 0 Gromov-Witten potential of local Calabi-Yau threefolds with some necrosity-distant partition function on R4, where this gauge theory is obtained by compactification of type 2A on this local Calabi-Yau, or on M theory on this Calabi-Yau, and that's if we have an effective theory in 5-dimension R4 times S1. So the Gromov-Witten potential is the necrosity prepotential in genus 0. And the higher genera give the corrections due to Omega background. Now, this is a very well-known story, but there's a lesser-known story that works in higher dimension. So if we take type 2A compactification on compactification in quotation marks on a Calabi-Yau fourfolds, this would compute again. Well, the effective theory is again some non-gravitational theory now in 2 real dimension less. And the genus zero Gromov-Witten potentials should compute some superpotential term for the effective theory on R2 times S1. But this is not the only way we can compute superpotential terms from the topological string. There's another way, which is by considering D4-branes wrapped on some Lagrangian. And but this Gromov-Witten potential for the special Lagrangian should compute, again, the same type of superpotential terms. So whenever we have a two-dimensional theory or a three-dimensional theory with an additional circle in M theory, that can be engineered in both ways, then we have a relation between enumerative invariants of exactly the type that I said in the previous slide. The open invariants are the local invariants. So here's the drill. Starting from a Looijenga pair X and D, we can do the following. We can replace a maximal tangency condition on one divisor, say the last one, say the conic, with a twist by OX minus DL. And we can replace the maximal tangency on all the other divisors by some open condition on some special Lagrangian near the divisors. Well, in the inverse image in this total space, OX minus DL. And the expectation is, well, the reason why we twisted just by one is that we will be looking at open Gromov-Witten invariants of special Lagrangians in the Calabi-Yau threefold, where we might have a fighting chance to define invariants, a la Solomon-Tukaczynski, for example. And the expectation of the previous two slides is that these open invariants are the same as the local invariants. And moreover, the open invariants are defined in higher genera, unlike the local ones. And they should speak in some meaningful way to the log invariants, refining the log local correspondence. So in formulas, we expect that the local invariants are equal to the open ones, and they obey the same VGGR relationship of the log local correspondence in genus zero. And in higher genus, there's a theorem of Bousseau and collaborators in the smooth case that allows us to give a precise expectation to how we should modify this prefactor to include higher genera. Essentially, the intersection multiplicity for the divisor that we twist by should be Q-deformed, and that's the relation that we expect. So I've just waved my hands for the last 5-6 slides. I just said that we start from a Looijenga pair. We would like to find some higher genus version of the local theory in terms of open Gromov-Witten invariants. And I haven't told you at this stage what the Lagrangian should look like, whether the Gromov-Witten count makes sense, and whether this conjecture has any fighting chance of actually being true. So let me make amends. And I'm going to restrict now to the case of the Looijenga pair with being tame, which, as I said, is not a huge restriction. It only rules out 3 examples. And my claim is that in this case, my threefold with special Lagrangians is a semi-projective Aganagic-Vafa pair. So I'm looking at singular Harvey-Lawson Lagrangians in a toric Calabi-Yau threefold. That's the claim. So again, about these Lagrangians, let me remind you about the Harvey-Lawson fibration. There's a million different ways we can represent C3 as total space of a algebraically completely integrable system. And one of them is the Harvey-Lawson fibration, where we take the moment maps to be equal to differences of square moduli of affine coordinates, the first 2 moment maps. And the third one is the image of the product of all 3 of them. Now, the generic fiber of this map is a cylinder T2 times R. So we have 2 compact circles associated to the first 2 moment maps, rotating the arguments of the affine coordinates with weights 1 minus 1, 0 and 1, 0 minus 1. And then we have a non-compact R from the third moment map, which is essentially, it parameterizes the real part of this product. And this is the generic situation, but there are special points on the base where the fiber degenerates, where essentially we strangle the neck of the cylinder to 0 size. And what we obtain is 2 copies of R2 times S1. And picking either of them gives what we usually call a toric A-brane in C3. And this picture can be globalized for the case of toric Calabi-Yau threefolds, there are symplectic quotients. So they are projective over their optimization. And so in the case of C3, the discriminant locus is just the union of the three axes in R3. And for a general toric Calabi-Yau threefold, we will have some metric graph in R3 with trivalent vertices and possibly loops. And if we forget about the symplectic information, the metric information of the graph, we can isotope this picture a little of the fibration over the discriminant locus to obtain some planar lattice graph. And from this, we can recover Y by taking the dual graph to this graph. The fan of Y is the cone over the dual graph of this planar lattice graph. So in this case, we're taking the conifold, O-1 plus O-1 on P1. And a singular Harvey-Lawson Lagrangian will sit on one of the edges of this graph. So these are the Lagrangians. What about the Gromov-Witten invariants? And I'm very happy that Melissa is here, so she can correct any wrong statement I'm going to make. This is probably the best scenario where we can define, and historically the first in Melissa's thesis, where open Gromov-Witten invariants of special Lagrangians in Calabi-Yau threefolds were defined in at least two different approaches, either by localization in Melissa's paper with Sheldon Katz, or by relating open stable maps to relative stable morphisms in work of Li Song and in the mathematical theory of the topological vertex of Melissa with Li, Liu, and Zhu. The upshot is that there is a moduli space of open stable morphisms to the special Lagrangian pair Y and L, where Y is a toric Calabi-Yau threefold and L is a Harvey-Lawson Lagrangian, a singular Harvey-Lawson Lagrangian of expecting dimension 0 for all genera. And it carries a virtual fundamental class, and we can compute higher genus Gromov-Witten invariants by computing its degree. And we can assemble those into generating functions, as we did for the log ones. So how do we do this? What does this look like for a tame Looijenga pair? So as I said, we twist by the second divisor, sorry, the last divisor, dl, and we replace d1 through dl-1 with special Lagrangian conditions. So in this case, Y will be the total space of O minus dl on the complement of the union d1 through dl-1. Our singular Harvey-Lawson Lagrangians will be incident to a torus 1 orbit intersecting the I in the compactification. And there's a canonical isomorphism of lattices relating absolute degrees in second homology of X with degrees in the relative homology of Y and L canonically, given by the inclusion of Y in O minus dl of X and the interpretation of winding numbers as intersection multiplicities. So for example, in the case of X and D being the line union conic, what we do is the following. We take, so the procedure is we delete the first divisor, D1, which is the line, and that's a toric divisor. So starting from the fan of P2, what we get is, we're just removing the hyperplane, the line at infinity, and we get a two-dimensional affine space. That's the fan of A2. Then we twist by the conic. So we twist by O minus dl. In this case, dl is C. So this is O minus 2. And this is a trivial bundle on A2. So the total space is just C3. And the fan is a cone over this diagram. That's a toric Calabi-Yau threefold, and the discriminant locus of the Harvey-Lawson fibration by reversing the construction a few slides back is to take the dual graph. And we get the graph of the frame vertex with one Lagrangian brain sitting on one of the edges. And this is the open Gromov-Witten theory, which we claim should be related to the log Gromov-Witten theory of the surface with the line and conic. So we have a setup of special Lagrangians in the toric Calabi-Yau threefold for any tame Looijenga pair. We have a working definition of open Gromov-Witten invariants for this special Lagrangians. How is this related to the log theory? And is this related to the way that was conjectured? And again, the statement is that the higher genus log theory of tame pairs and the open Gromov-Witten theory of the associated special Lagrangian pair are closed form solvable for all tame Looijenga pairs. There's a master formula from which the case of a generic tame Looijenga pair descends. And in particular, once we have that, we can ask ourselves whether our conjecture was true or not, and the answer is true. And the proof is either the worst or the best you can hope for. The proof is combinatorial, and the reason why this is combinatorial is because different contributions from moduli spaces in different genera are involved in the left and right hand side. So it turns out to be more economical to make a statement in terms of generating functions. And the way we achieve this is, well, on the log side, as I mentioned, is by taking the Q-deformed version of the scattering diagram for X and D. And on the open side, we can compute the open Gromov-Witten theory of Y and L using the topological vertex. And so, for example, I'm not sure I have time to discuss this in very much in depth. The sort of tropical-like calculation we reduce to for P2 with a line and the conic is we can use the birational invariance of log Gromov-Witten theory to use a circus of Lake construction of sorts by blowing up points in some divisors and then contracting some curve. And we end up with, starting from P2 with a line and the conic, we can end up with the second Hirzebruch surface relative to the toric boundary, for which the calculation of log Gromov-Witten invariance is essentially tropical. It's a count of graphs in the fan of F2. And the result of the scattering calculation in this case, if you're familiar with it, is, well, the result of parallel transport across a wall and the known relation of this to log Gromov-Witten theory allows to extract exactly the central binomials 2D choose D that I showed in the table at the beginning. And the Q deformation amounts to just taking the Gaussian binomial coefficients, again, the central ones in the setup. And possibly in a setup that's very familiar to many of us, the dual open Gromov-Witten setup is just a frame vertex, which for reasons that I won't be able to explain is framing 1. So we know that topological vertex with a single Lagrangian on one leg in the representation basis given by a Schur function in the principal specialization. And when we move to the conjugacy class basis by trying to extract, when we want to extract the Gromov-Witten invariance with fixed winding numbers, there's a known change of variable for this, and application of the Q binomial theorem returns from, if you want the Chern-Simons calculation, the Q deformed central binomial coefficients time some prefactor. And if you plug this in the conjecture, you get the result of the previous slide. And you take Q tends to 1, and you get the table of I showed you about the counts with the boundaries on line and conic. So this is a bunch of implications that I'll describe in the next 7 minutes for many things that we know at this conference for log Gromov-Witten theory and local Gromov-Witten theory, which are subjects that are slightly more distant. So essentially, we have an immense toolkit that's very familiar to us that can solve problems not very far from us. So for example, if we start from a tame Looijenga pair, again, the plane with line and conic with maximal tangency conditions, or the local theory, O-1 plus O-2 on P2, we can assign to this a large and dual Chern-Simons theory interpretation from the threefold. We have all genus calculational scheme in the A model, either by localization or by the topological vertex. And we have a unitary Hender-Mission random metrics model interpretations, again, for this Gromov-Witten problem of surfaces. which we can reinterpret in many ways. Like we have a crystal melting picture. We can interpret this relative Gromov-Witten theory generating functions in terms of VIVs in a free fermion model. And they coincide with tau functions of known integrable systems for certain specialization of the times. They're all rational reductions of the two-total hierarchy. And we have famously a role for the topological recursion in this context due to BKMP, Leonardo-Rontin, and Boan-Fang and Melissa Ingenu, who are here in the audience, reconstructed this relative Gromov-Witten invariant from the topological recursion on some spectral curve that we can read off from the toric Calabi-Yau threefold. There's a hidden integral structure in terms of open BPS counts. So Aganagic-Vafa invariants, which is not apparent at all in log Gromov-Witten theory. We have a reformulation in terms of a symmetric Quiver-Donaldson-Thomas partition function, again, invisible from the geometry of the surface. And we have some gauge theory interpretation for this generating functions in terms of surface defects in a four-dimensional gauge theory. So you name it, we have a lot of things that we can hit this almost classical geometric problem with. And so why not do it? Say for the P2 with the line of the conic, this generating function is the extremal limit of the color Holmes of the unknot at framing 1. It's a resolvent of some matrix model. It's some limiting version, some double scaling limit of the Stieltjes-Wigert matrix model. It's a tau function of discrete KDB and the Volterra lattice. And if we sum the omega G1s of this spectral curve, which is a spectral curve of the vertex at framing 1, we have an H bar to the 2G minus 2 to sum over, and we change variable to Q equals E to the I H bar. We can relate those to our log Gromov-Witten invariants at higher genus, and it can be computed at Q equals 1 in terms of Donaldson-Thomas invariants of the two-loop quiver. So this is amazing. There's a lot of things. This is basically a solution in search of a problem. And I've already explained the uses of, all of these have some use, but I would like to isolate those that are helpful to teach log and local Gromov-Witten theory people, things that they didn't know before. So we've already seen the use for a topological vertex that gives us a proof of the higher genus log open correspondence. And in the remaining 4 or 5 minutes, I'm going to find the role for some new results coming from point 6 and 7. So the open BPS interpretation and the Quiver DT1. So I have 3 applications to mention. So first of all, the as was done for the case of Calabi-Yau threefolds, we can extract hopefully conjecturally integral invariants from the Gromov-Witten genus 0 Gromov-Witten count by some BPS type change of variables. So we can define a sequence of a priori rational numbers from the result of the genus 0 local calculation, which is the only one that makes sense, by generalizing the multi-covering formula that we would have for Calabi-Yau threefolds. And by plugging the log local identity, we can state this as some sort of, again, BPS type change of variables involving the log invariants. The conjecture for L equals 2, so for 4 folds, a conjecture was made by Clement Pandaripande in 2007 that these should be integers as their Calabi-Yau 3 counterparts. And Yunel and Parker formulated this conjecture in higher dimension and provided a symplectic proof for compact Calabi-Yau n-folds in any dimension greater than or equal to 3. So what do we learn from the log open correspondence, the proof of the log open correspondence, and it's, well, in genus 0? Well, we know that the local invariants are equal with prefactor equal to 1 to the open invariants of some Calabi-Yau threefold with some Harvey-Lows and branes in it. In a case in which our Calabi-Yau n plus L fold is realized as a local surface, as the total space of rank L vector bundle on surface coming from a Looijenga pair. And Auguri and Vafa and Labastida, Marini and Vafa define open BPS invariants exactly by the same formula of Clem, Pandari-Pandey, and Unell and Parker. So the omegas, the open and local omegas, are related to the open and local ends by the same formula. And the Gromov-Witten invariants, the ends coincide with each other by the log local principle, log local open correspondence. Therefore, we get to the point of establishing an equality between the omegas, the closed BPS invariants, the Clem, Pandari-Pandey invariants of local fourfolds, for example, and the Oguri-Vafa invariance of a threefold with a special Lagrangian L. And what do we know about the latter? Well, there's been a lot of work by Sulkowski and collaborators relating these open BPS invariants to the Donaldson-Thomas invariance of a symmetric quiver, which can be read off combinatorially essentially from the fan of Y. In the case of P2 with a line at a conic, this quiver is just the quiver with one vertex and two loops. And what do we know about the latter, where there's a theorem of Efimov that these Donaldson-Thomas invariants are natural numbers. So up to a sign that's popping up in this formula, the absolute values of the omegas are equal to the Donaldson-Thomas invariance of the quiver. We know that these are integer, and we don't need to make any effort to prove this corollary. This follows what the hard work has been done elsewhere in the proof of the local correspondence, log local open. So that's what happens in the case of P2 with a line at a conic. The KP invariants of O-1 plus O-2 on P2 are computed as the DT invariants of the two loop quiver. And there's the quiver for any local Calabi-Yau 2 plus L fold coming from a Taylor-Looijenga pair. Moreover, I think I have only 2 minutes now. There's been a lot of effort recently in trying to define Donaldson-Thomas invariants of Calabi-Yau fourfolds, either in terms of Gieseker semi-stable sheaves or stable pairs. And it was conjectured by Kalmalik and Toda that conjecturally these definitions should reproduce the omega D, the Gopal-Kumar-Vafa-like BPS invariants of Clem and Pandari-Pandey. And so how to check this? So those defined by the multi-covering formula. And checks were performed by solving explicitly for the left-hand side of this equality by Calcul and Monavare. And the equality hinges on the result of the log local correspondence for the right-hand side for these omega Ds. And finally, this is only about BPS invariance in genus 0, but there are refined generating functions taken into account contribution from higher genera, and there's an integrality result that can be established for those, leading to a refined integrality statement for the higher genus log Gromov-Witten invariance. And this follows from a direct arithmetic proof from the log open calculation. Final thing I want to say, everything I said by saying X variety can be generalized to X a Deligne-Mumford stack, a smooth Deligne-Mumford stack. And instead of having 18 smooth deformation families, we can have an infinite list just by playing with the order of our singularities. So one example is we can take X to be the weighted projective plane, D a toric divisor intersecting the point with the torus fixed point with stackiness Zn, and D2 the union, a smooth member of the union of the linear system generated by the other toric divisors. And we can run through the local open construction. And for example, the quiver we get is the n+1 loop quiver in this case. So the conclusion is that for Neff and Taylor-Looijenga pairs with varying degree of generality, the log Gromov-Witten invariants are the local Gromov-Witten invariants for Neff. And for Tame, they're equal to the open Gromov-Witten invariants of an allied theory of special Lagrangians in a Calabi-Yau threefold. And up to a BPS type change of variables, these are Donaldson-Thomas invariants of a symmetric quiver. And Clem, Pandari-Pandey, Unell, Parker, Labastida, Marino, Oguri-Vafa BPS invariants in the respective contexts. And moreover, we can use what we know about one to rule them all. So all these invariants are closed form computable and are in fact computed. There's a master formula that takes into account all cases. And I'm over time, so I should stop here. I have a bunch of questions of my own, and I'll be very happy to.
Okay, yes.
Thank you.
It's time to stop. So yes, let's thanks Andrea. Yes, Piotr. Questions?
Hi, nice to see you. Can I have a question?
Yes, yes, sure.
It's time for that. So I'm wondering if there is a place in this setup that you have for refinement in the spirit of omega deformation. Or with, let me just advertise, take this opportunity. I had a paper with Sicheng recently where we generalize this relation to quivers that you mentioned for this local manifolds to this refined setup, and this quivers fits nicely also with the statement of Efimov that you get positive invariants. So that's why I'm asking.
I don't know what the log counterpart of that is. So I should probably say that in the case of the smooth divisor, which is the complement of the setting that I've been considering in this talk, Busso has a paper relating this to not the higher genus, not the self-dual omega deformation for the corresponding Calabi-Yau3, because if we have a single divisor, we're considering O minus that divisor on, say, P2. There's an interpretation of the, as a matter of fact, a worksheet interpretation of the Nekrasov limit, sorry, the Nekrasov-Shadishvili limit of the refined topological string in terms of the log invariants. So the log invariants really should be thought of in that context as giving the quantum B period for the NS deformed B model on that Calabi-Yau3. But that's still one parameter. I don't know how you can so first of all, there's a question why we get the self-dual guy here and not the NS one, and there's an answer to that, which relates to the fact that all of these toric Calabi-Yau3 folds have no compact divisors, so they have trivial fourth homology, and there's a close relation between higher genus and NS in that case. And other than that, I don't know how to push the log story away from the NS limit. So I don't know how to add that extra parameter in that context. It would be extremely interesting, but while there is a worksheet interpretation for the NS, limit of the topological string on a local Calabi-Yau3, there's no analog of that away from that limit.
See. Okay, thanks for a nice and some inspiration.
Yes, so we are way behind the schedule, and if someone have one short question, yes. If no, let's thank Andrea again. And I think that we'll continue. So let's stop recording of this talk, right? And